Hello, differential equation students, and welcome to unit number 5. Okay, this is our final unit. This will contain sections over chapter 6. And what we're going to do in 6.1 is we're going to review some power series, which you should have seen in calc. Okay, you should have definitely seen these in calc 1 and 2. We didn't do these in calc 3. So I'll just remind you kind of the general linear second order equation, right? This is what we would have, some differential equation. That's not too hard, right? The big thing is, as we're moving down through, is we only learned how to solve these if these things right here were constants or polynomials of like some degree n, right? And what's going to happen is these might be coefficients of the dependent variable. So like you might have like y squared sitting in here and things like that, okay? And if it's any type of polynomial, then we have this issue, right? So this is no longer necessarily linear, and we're going to need some power series, all right? And that's the whole premise on why we need these power series. So thinking about power series, a power series, by definition, is in x, right? So we usually think about it in x, where the x is the independent variable, and you do it about a point. Okay, you do it about a point, which is why like x minus a is here in my little summation, and it's in the fact it's a factor of the form like this, right? So I have some summations to a power. Of course, that's where we get like this power series, where we have c sub n is an element of the real numbers. I don't think you guys necessarily learn this a lot, so I'll just reiterate here. This is real numbers. Okay, those are all the real numbers. Specifically, what you've seen in the past is you've seen Taylor series. You have seen a Taylor series, okay, where we take f to some power n of our a, right? So this could be about a number. It could also be about a variable. And then we have the n factorial, right? And we also have this n here. We've seen this. You have a very common one is this one, right? E to the x is a very, very, very famous Taylor series, okay? Which we've had a lot of answers with e to the x, so we should anticipate having to use this one here quite a bit. We've had e to the x, okay, many times. What other things have we had? Well, if you think back, we also had x to the n power, right? We've had something that looks like this before, okay? And when we're thinking back, oh, well, this is like a classic geometric one, okay? And again, it can be described by this one over here. It says, of course, these only work on an interval of convergence. So we see, okay, but differential equations are always on an interval of convergence, so we're good to go, right? We're supposed to technically like have some type of interval. Like I started out very strong with this, and then I've kind of trailed off, but like 0 to infinity, or I could include 0, right? We've done intervals of convergence before, okay? And we always pick the largest one, okay? What you're going to get in class is a list of well-known power series, okay? These 8 well-known power series. I will print this off and I will give it to you in class next time, okay? You will have this list here. You will also be able to have this on the test. So the very first one that I want to do is I want to talk about finding the convergence of a power series using the ratio test, okay? Using this thing called the ratio test. And if I'm using the ratio test, I should probably list it out. So this is the limit as n approaches infinity of the absolute value of c sub n plus 1 x minus a to the n plus 1 power divided by c sub n x minus a to the n power, okay? Now, when you see this, right, we could do a little bit of simplifying. We can simplify this down a little bit. Absolute value of x minus a, the limit as n goes to infinity. That's a terrible n here. Let me change it. N goes to infinity of c sub n plus 1 over c sub n. Right? And I don't think that's a hard solve, right? I mean, this n down here, this whole thing right here, would essentially cancel out with this one up here, right? Or I'm sorry, I probably shouldn't have drawn it like that. It should cancel out with this one here, right? Because I can split them up and it becomes a multiplication. So I have this x minus a, and then I just make sure that this is a positive number. So then I pull it out as the positive, and I'm left with just this over this, right? And we call that like the big L here. Okay. So that helps us to start it. Now, if the series is of the form summation from n equals 0 to infinity c sub n of x minus a, of course this is a power series right here, right? That's the definition there. Then it converges if L is less than 1, diverges then if L is greater than 1, and is inconclusive. If L equals 1. Okay, so basically, when you plug this stuff in, right, if I get this L, this limit here, and it's less than 1, then the series is going to converge to some point. And if it's greater than 1, it's going to diverge, and then it's inconclusive if it's equal to 1. Okay, so what we're using, right, is it said to use the ratio test. Well, I'm describing the ratio test, right? Now it says find the convergence, okay? Well, if you're going to find a convergence, right, we should probably know something about like this thing called a radius of convergence, okay? The radius of convergence is always the distance from the midpoint of the interval of convergence to one of the bounds. So when we have an interval of convergence, basically like I'm cutting that in half, okay? Essentially is what that's saying, right? If I have an interval of convergence and I want to find the radius, right, of convergence, then I just need to take the interval and I need to cut it in half. So let's start out with an easy example. If a power series has an interval of convergence of -1/2, let's say, till x, I'm sorry, x is between -1/2 and 5/6, and I want to find the radius of convergence. I mean, I hope that this isn't too bad, right? From -1/2 to 5/6, how much ground has been covered? Well, again, this math here should be very straightforward, right? -1/2, because it's on the negative side, I need to take 1/2 plus 5/6 to get the length of the interval, right? And if I'm doing that, that should be, I think that's 8/6, which of course is 4/3, right? And it's 4/3 units, like long or wide. Well, if it's 4/3 units long, then half of that, right, would be the radius of convergence, which makes it 2/3 is the radius of convergence. Okay. So there's our first one that's dealing with the radius of convergence. Now we have an example where it says find the interval and radius of convergence for this power series. So now would be a great time to pause the video and make sure you get it written down. Okay, so now that you've had enough time to write this down, I'll remind you that we're going to be using the ratio test to perform this, right? We want to use the ratio test, okay? And here when I'm thinking about how to do this, if I remember the ratio test, it shouldn't be too bad. The first one that I need to do is I need to plug in like the n plus 1, right? I'm getting, it was c sub n plus 1. So here I need 1 over n plus 1 squared. And then that's times x to the n plus 1. So this first one, right, this red one is c sub n plus 1, right? And I saw that on the top. And then it's supposed to be divided by, get another one, that's supposed to be divided by c sub n, which would be 1 over n squared x, oh, I put squared, x to the n, right? Which is straight whatever this is, okay? Now, it'd be nice if we could simplify this a little bit, right? Manipulate some powers and things of that nature. Well, it's 1 over n plus 1 squared x to the n plus 1 times, if I bring this up top, that's n squared over 1, and then I would have x to the negative n. Of course, you could drop it to the bottom if that helps you out. But simplifying it, I don't think will be too bad for me here. Because I get what these, let me get a different color so I don't confuse anybody. This n and this n will cancel each other out, right? So what would I have? Well, I got the x, then I have n squared, I got this n plus 1 squared, and I don't think I can really do anything else. Like, so here we have like an x, right? Well, the x stuff was supposed to come out and be absolute valued. So I just have x left, or I should say this all canceled, but this x is left because of this 1. Now, and then its limit as n goes to infinity of the c stuff. Well, the c sub n stuff is n squared on top, this one right here, and then on the bottom I got this n plus 1 squared. And now what I'm trying to think of, right, is clearly they're sharing, right? They're sharing like this squared idea, right? So I might, like, they don't really cancel out, but essentially they're going to cancel out there. So I have the absolute value as the limit of x, and then n as the limit, or n approaches infinity, of n over n plus 1. And now what you need to think about, right? It's a terrible n. I just really don't want you to copy it down wrong. Okay, now what you're trying to think about is as I plug in n, right, and n gets bigger and bigger, the top gets bigger and bigger, so does the bottom, right? Well, will the top ever take the bottom? Well, it won't, right? It'll always be like 1 short. Obviously here it's going to be 1 short, so it's going to get really close to 1, right? This thing right here, this thing gets really close to 1, but it doesn't quite get there, right? So I'm taking something that's gets closer to 1 but doesn't get there, times by x. So really the absolute value of x is less than 1, right? Because here this thing is getting closer and closer to 1, it won't ever hit it, so it has to be less than 1. Okay, it has to be that less than 1. And then when I have it less than 1, we've done things like this before. If you just solve that like you're back in algebra 1, you'd get what? X would have to be between -1 and 1. Okay, so that is actually the interval of convergence right here, and it has a radius of 1. Okay, and I'm going to do one more on this video here, another interval and a radius convergence, and then after this one we're going to get into changing indices and manipulating actually the summation part here and things like that. So there'll be 3 other videos for that. I'm going to do one example of each one. Okay, I have 3 examples for those, and that's going to prepare us to be ready to try to solve using power series in 6.2. But I should have stalled long enough for you to have a chance to write that stuff down. So now here, when I'm looking at it, right, I think I could probably change kind of how this thing looks just to help me out. Like, this is the summation, k equals 0 till infinity of 4x minus 5k divided by 3k, right? Again, here we do the plus 1 first. So if I'm doing the n plus 1, I would have my 4x minus 5, and it's not n anymore, it's a k, so just know that. So it's k plus 1 here, and then divided by 3 to the power of k plus 1. Then I'm taking that and I'm dividing it by the regular one, right, this thing over here. So I'd have 4x minus 5 to the k divided by 3k. And again, from here, you know, you can choose to do it however you'd like, but I'm going to probably rewrite this so it makes sense to me as k plus 1, 3k plus 1 times the bottom, right? Well, it's a reciprocal, so this is 3k over 4x minus 5k. And now I'm hoping that I can start like canceling some things out. Okay, this k, 3k is going to go with this one. I have, all of this goes with this one. So this has x's in it, so I might as well just pull that out now. That's 4x minus 5. And then I have the limit as it's a k goes to infinity. The absolute value of, well, if I pulled that out, what's left? There's no k's, right? There's a 1 up here. Oh, and there's this 3, so that's 1/3, right? Okay. Here, as we try to solve this one out, I wonder, like, as k increases, does it do anything to this? Well, no, it stays as 1/3. So I have 1/3, and then this needs to drop down, right? Now, if I wanted to converge, right, it does say interval of convergence. It converges if it's less than 1. So, like I did up above here with this less than 1, I need this to be less than 1. Okay, well, now just solve this, right? Multiply by 3, I'd get 4x minus 5 is less than 3, right? Or it's greater than -3 to get rid of the absolute values. And then, you know, classic solving here, right? Hopefully this is all a piece of cake for you. And I get x is between 1/2 and 2, right? This is known as the interval of convergence. Well, usually we have a radius as well. So if I find the radius, that's an awfully big R. The radius of convergence, well, I'd have to find the distance between that, right? So that's what, 1.5. So it's a 1.5 from 1/2 to 2, which is 3/2. Then cut in half would be 3/4, right? So then I have, this is my answer. Okay. So anytime it asks for the interval of convergence, just remember that you need this part here to happen, because over here we wanted it to converge, right? If we want it to converge, right, we have to have L being less than 1. Okay. And that's going to complete the first video. All right, coming up, three other videos, and we're going to work with manipulating summations like these. Okay, we're going to be working with manipulating the indices, so like this k and things like that, as well as manipulating this inside.